And we have two other configurations. It's nothing very complicated. This is something called half-bridge circuit, and we have two strain gauges. So for example, if we were to use a beam and you pull that beam down, and we have one attached at the top and one attached at the bottom. And the top one is going to be stretched, right, as you pull this beam down. On the other hand, the one at the bottom is going to be shrink down or compressed, right? And if you apply that on here and you apply R3 down there, then, and if we assume R1 is same as R2, then our strain value is going to be now 2 times delta V over VE divided by F. Previously, it was 4 times delta V, right? Now it's 2 times. And what I want to emphasize here is don't get fooled by this number 2. So we are measuring the strain, right? Let's assume we have 2 identical beams, one beam here and the other beam. They are identical. And you have one strain gauge on top here, and the other beam you have strain gauges up and bottom. And you are applying same force. Because these two are identical beams, if you apply same force, then it's going to bend exactly the same, right? So we are measuring the same value of strain using one sensor or 2 sensor, right? So basically speaking, you're measuring something same, but you are using 2 sensors. So the output voltage is going to be 2 times of single strain gauge configuration for this case. It's very natural, right? And that's the reason why for a quarter bridge circuit, we have number 4 in front of there. And for a half bridge circuit, we have number 2, because this voltage we measure is going to be doubled. And we can write it down using an equation. So here, this was the configuration of a quarter bridge circuit, right? And then we can write this same equation as 2 times VE 1 over F. I just divided this 4 into 2 times 2, right? And then we can just call this 2 delta V as delta V2. So delta V2 is 2 times delta V. This delta V is output voltage measure from quarter bridge circuit, and this is V out from half bridge, right? So your output voltage is doubled up from what you get from a quarter bridge. So like I said, you're measuring same thing, but you have 2 sensors here. So the voltage you're getting is just simply doubled. You are measuring the same strain, so this is very small, so you need to multiply 4 to make this guy. On the other hand, this guy is large, so you have to only multiply 2 to get this. And here it gets even clearer. If you have 4 strain gauges, 2 on the top, 2 at the bottom, and then you apply these 4 strain gauge in a configuration that the top ones are facing each other like that, cross, and the bottom ones are like these, then your V out, your strain equation is going to be 1 times delta V over VE divided by F. Why is that? Because this delta V itself is very large. We are measuring the same thing from 4 sensors. So the voltage is 4 times greater than what you have from a quarter bridge. So you don't need to have 4 here. It's just going to be 1 because this guy is already 4 times larger, right? But still, delta V is too small to measure. So we're going to use a voltage amplifier. And here is why we kind of learned about those, inverting or non-inverting amplifiers. We move on to the next page. This part is talking about signal amplification using differential amplifiers. So here is the circuit configuration. It's slightly different from what we've seen from the inverting or non-inverting, but it's a very, very small variation from what we did. So let's see what's the difference. And like I told you guys before, if you do this 3-step thing, use the ideal op-amp assumption, then do the KCL at the negative node, then find all the components and apply that back into KCL, you're going to find your governing equation. And let's see how this works. So the ideal op-amp assumption we use is V positive is same as V negative, right? And the input current is 0. So the current that flows in here is going to be 0, and the value here and the value there are going to be the same. Next step is to do a KCL at the negative node, which is here, IN, IF, so 2 flowing in, 1 flowing out. And then what we need to do is we need to find these I values, right? So first, let's find what V positive is, because that is going to be same as what we see for the V negative. So V positive is the voltage at this node, which is related to the input voltage you apply here. Because think about it, this is a circuit that you have a voltage source and 2 resistors, right? So from here, you can easily find the voltage at V positive, which is V2 times R3 over R1 plus 3. No, R1 plus R3. And that is going to be same as V negative based on our assumption, right? And our KCL is IN is I1 plus IF. These 2 are going in. This is coming out of this node. And this guy is 0, right? And I1 is current here, which is from here to there, right? Across a resistor. So that's very simple. V1 minus V negative divided by R1 plus IF is also simple too. IF is V out is here, right? To V negative across a resistor. So V out minus V negative over R3. So from this equation here, which is 0, we have V1, R1, V out, R3. We all have these, but we don't have V negative. But V negative is same as V positive, and V positive is this value. So if you just plug those in here and there, plug this here and there, right? Then we can have an equation like this, and it boils down to R3 over R1, V2 minus V1. So that's the reason why we call this as a differential amplifier. The difference between 2 voltages at here and there, V2 minus V1, is being amplified to our output Vout by a ratio R3 over R1. And one thing to note is if V2 is 0, our Vout is going to be negative R3 over R1 times V1. If V2 is 0, then it's negative R3 over R1 times V1, right? So this is an inverting amplifier. And let's see if this is the one. Say V2 is 0, so we get rid of V2, like that, right? Then this is an inverting amplifier. The way you can easily tell is your only input source is being fed into the negative node, right? Your positive node goes to ground. It's nothing. So input goes into negative, so it's an inverting amplifier. And we can see a relationship like that. So this differential amplifier is nothing but a very simple variation from the inverting amplifier. And since this circuit is amplifying the difference, V2 minus V1, the environmental noise that is in common can be removed and amplified. What I mean here is, let's say for these two voltages, there's a noise coming in commonly into here and there. And if you find the difference between these two, then that noise that is in common here get canceled out. And we can very simply see from an equation, Vout is R3 over R1, and it's difference, right? V2 plus noise minus V1 plus noise. It's a common noise. So they just cancel out. And it becomes R3 over R1, V2 minus V1. So that's a good benefit of using this circuit, because you see again, if there's a common noise affecting both input nodes, those can be canceled out, rejected, and you are having your output that is just purely the difference between two inputs. So finally, we are here. We have our strain gauge. We have our strain gauge here and the Wheatstone bridge. This, we can have a potentiometer or variable resistor, right? But anyway, we have our Wheatstone bridge with a strain gauge, and we have our input applied, excitation voltage. Generally, it's 5 volts DC. And then we have measurement node that is Vout here. And then the difference between these two is being amplified by this configuration. And we are finally looking at the amplified voltage. And let's make this a small change. Let's not call this Vout bar. This is Vout, and let's call this Vout bar, okay? And this is the amplified voltage. So this is going to be the final configuration that you may want to use for measuring the strain. We could have measured the strain directly from the beam itself, right? Or whatever structure, mechanical structure we have, but that's very difficult. So we use a strain gauge to measure the resistance change, but that was, again, difficult. So you form a Wheatstone bridge and measure the output voltage, but that was difficult too. So you amplify. And you are getting a measurable voltage.